Hello guys and welcome back to Mr. G Physics. Here's Mr. G and we're going to be making another video for the grade 12 related to momentum and impulse. This time Newton's second law in terms of momentum and the definition of impulse. Subscribe for the channel if you didn't do yet and I'll see you in a minute. Well, now, as we say, we're going to be focusing on Newton's second law in terms of momentum. We're going to look at the definition of the impulse, and we're going to look about the relationship between impulse and change in momentum, which we did in a previous video. I'm going to leave the link below. Now, at the end of this video, you're supposed to be able to state Newton's second law in terms of momentum, know the formula. You're supposed to define impulse. You're supposed to look at the impulse momentum theorem, which is the relationship between impulse and change in momentum. And we're supposed to be able to explain some safety precautions in terms of momentum, or Newton's second law in terms of momentum. All right, so without delaying more, let's start with Newton's second law in terms of momentum. Now, I want to recall something that you did previously in previous grade, which is Newton's second law of motion. Remember, in grade 11 or previous grades, you did that net force was equal or is equal to mass and acceleration. Guys, this is Newton's second law. This is Newton's second law of motion. And now, in other words, in that law, you learned that acceleration was directly proportional to the net force, and the acceleration was inversely proportional to the mass of the object, not to mass. That is what you learned in previous grade. Now, this time we're going to look how this law is related to momentum, or how momentum can be related to this law, and then is what we call Newton's second law in terms of momentum. This law, in terms of momentum, states that the net force is equal to the rate of change in momentum. Before we even moving on, I want to point out the word rate. Guys, whenever you see the word rate, and you're going to see it a lot in physics, believe me, that means that you are going to divide by time. So the word rate means dividing by the change in time. So it's the rate of change of momentum. In other words, this means that it's change in momentum divided by time. And that is what we call rate in change of momentum, or in momentum. All right, and that is equal to the net force. So the law is quite simple. It states that the net force is equal to change in momentum divided by change in time. This is a vector quantity. I want to emphasize that you won't be penalized if you, I don't need those colors. You won't be penalized if you don't use the vector notation, but it's a vector, so I'm going to place it anyway. So this is Newton's second law in terms of momentum. We know already previously, in the previous video, we know that the unit for momentum is, or change in momentum, is going to be kilograms meters per second. We know that the unit for time is seconds. I'm speaking about the international unit. And we know that force, because we've done a lot of work about force, the unit is the Newton. So now you have all the units that you have. But I want you to note something which we eventually going to speak more in this formula, which is that the net force is inversely proportional. Let's say not inversely proportional, but they are related. So if the time becomes smaller, the net force becomes bigger. I want you to point out it's not exactly in a relationship like you say, okay, if the time increases 2 times, then the force decreases by so many times. No, not exactly like that. Let me not do this one, but you need to know that they are inverse, they are related in an inverse way. So if the time is greater, the force is smaller. If the time is smaller, the force is greater. We're going to point that one a little bit later. It's a very, very important point here, but they are not necessarily in a relationship. Like if you increase the time 2 times, then the force will decrease so many times. It's not like that, but that is important to point out. The one that to write. Now, this force in the exams you'll get, it will be not written like this. It will be net force multiplied by time equal to change in momentum. This is how you are going to get it in the exam. That's why I want to write it like that, because that is how you will look at it. Let me just maybe highlight that one so you can see. You will see it in that way in the exam. Guys, let's see one very easy example to know how to apply this Newton's second law in terms of momentum. I don't want to make the videos that long. There's a soccer ball of mass 0.5 kilograms. Remember, I like to extract all the data. So we're going to do the data. The way in which you take the data out of the question is entirely up to you. You can write it down, say data, very organized, or you can do a picture and write all the data there, or you can extract that you read. That is what we're going to do. So we're going to say data, and then they say a soccer ball of mass 0.5 kilograms. So the mass of that ball is 0.5 kilograms, move with a velocity of 12 meters per second towards a soccer player. So now, before we even write the velocity, we're going to select direction. It means it's moving towards. We're going to take towards, and let me just take the other color. Towards is going to be positive for us. All right, so everything that is a vector quantity and is moving towards will be positive, and everything that is moving away will be negative. In other words, the initial velocity of this specific ball is going to be positive 12 meters per second. I highly recommend you to do this one in this way while you're taking the data towards the soccer player. Just before the soccer player kicks the ball, when the soccer player kicks the ball, it moves with a velocity of 15 meters per second in the opposite direction. It means that the final velocity of that soccer ball is equal to negative 15 meters per second, because it's in the opposite direction. It's away from the soccer player. Calculate the net force that is part of the data. Net force is question mark if the ball is in contact for 1,2 milliseconds. So the time, guys, is equal to 1,2 milliseconds. We cannot work in milliseconds. Milli, like millimeter, milligrams is 1,000. So you have to divide by 1,000. That one will be 1,2 divided by 1,000, and this one is equal. Let me make sure I did all this calculation, but I want to and make sure you get that this one is equal to 0,0012 seconds. That is going to be the time. So now we are going to calculate for the net force. Guys, what we are going to apply? We are going to apply Newton's second law in terms of momentum. Now, as I said, I recommend you to write it in the way that you will get it in the exam, and you must get used to that one. So we have the net force multiplied by the time is equal to change in momentum. Now, we don't have change in momentum. We previously learned that change in momentum is equal to the product of mass by the change in velocity, final minus initial. That is how we calculate the change in momentum, and we are going to substitute that formula in there. So if we do that one, we have that F net multiplied by the time is equal to mass bracket final velocity minus initial velocity. And then the rest of the question is just substitution. It's really simple. So F net is what you are looking for. Note, F net is a vector quantity. I didn't mention because it's something that we know from previous grades. Multiplied by the time, I'm going to open bracket 0,0012 is equal to the mass, which is 0,5. And now, very careful, look at the direction of the velocities in the data we extracted. So the final velocity was negative 15 minus the initial is 12. So this is what we have. Let me fix the 12 for you all. So 12, a close bracket, and the rest is just calculation, which I'm going to do right now. I did all the calculation, but I want to make sure once more is minus 12. This is equal to minus 27 times 0,5. This is very easy a calculation, guys, and then divided by 0,0012. You get the final answer for net force is equal to negative 11,250 Newton. Note the following. That minus means direction. That is the final answer. However, I highly recommend you to take the negative and write the direction in words. For instance, it will be 11,250 Newton, and I'm going to write away, my goodness, away, just away. Or you can write in the opposite direction. And this is how we apply Newton's second law in terms of momentum to a simple question. It is going to be like this in the exam. So now let's go to the new definition, which is the impulse. Now, impulse, another very easy definition you're going to be doing is the product of net force and time. So impulse is the product of net force acting on an object and the time the force is acting on an object. So in other words, the product of F net, let me maybe, just maybe, use this color. The product of F net and the time, that is what we call impulse. Right. Now, for impulse, the most common symbol internationally speaking is letter J. Letter J, it is a vector quantity, so I'm going to add the symbol of the vector on top. But sometimes you can also find that I is being used. My recommendation as your teacher, what symbol you are using at school, don't use my symbol, guys. Use the symbol you're using at your school in your province, all right? So now we can say that impulse is equal to the product of F net multiplied by the time. That is what we call impulse. And I'm only going to point out that it's a vector quantity. So it means it has magnitude and direction, the same as force, the same as momentum. All right, so that is impulse. But now, something else before we move to the next part, which is the unit. Well, the unit for force is the Newton. You know that. We just spoke about that one. The unit for time is seconds. So the unit of impulse is the product of Newton and second. It's a product. It's not a per. It's not Newton per second. It's Newton second. We read in that way. That is the unit for impulse. It's quite simple. Now, if we go to Newton's second law in terms of momentum, and I want to go, this is a theorem. If we go to Newton's second law in terms of momentum, look here. We have the net force multiplied by the time is equal to change in momentum. All right, that is Newton's second law in terms of momentum. But guys, look here. This is the impulse. We just speak about that one, product of F net and time. So this one here is the impulse. Guys, this is what we call impulse momentum theorem. We can see that impulse, and I am going to use the symbol, impulse is equal to change in momentum. In other words, if you want to calculate the impulse of a force, you just have to calculate the change in momentum caused by that specific force. So this one is impulse is equal to, if you want to substitute, this one is the product of mass bracket final velocity minus initial velocity. Guys, this is what we call the impulse momentum theorem. It's quite simple. Now, I want to point something in terms of impulse. Sometimes you will get graph. In actual fact, for sure, you may get graph throughout the year related to this specific topic. If the graph is about force versus time, so that is one of the first things you have to look when you are working with any graph, is what is the graph. This one is force and time. So if you get a graph of force versus time, doesn't matter the shape, you need to know that the area under the graph will be equivalent to the impulse. So this area here will be equivalent to the impulse of that specific object, the impulse caused by that force. So that is important. I did write it here on the right. In this case, it's a triangle, but guys, it's not always a triangle. So impulse is equal to area. Area under, area under the graph. For instance, for example, in this case, the impulse will be equal to half base times height. Because it is a triangle, not always is going to be a triangle. Now, this graph is force versus time, but later on you'll see graph that there is not force versus time, but rather just a momentum versus time, for example, which is quite simple. But here I wanted to point that one out. And guys, To finish, let's speak about impulse and safety consideration. That is the point where I said to you we're going to speak about that one in a minute. From Newton's second law in terms of momentum, but we're going to write it in this way. Change in momentum divided by change in time. Rate in change in momentum. Now, there are some safety figures that can be done due to this specific law. For instance, seat belts, and I'm going to highlight those. We have seat belts, we have airbags, we have crumble zone, and we have even more. When we play in cricket, for instance, and a fielder hold the ball, it must move back the hands, otherwise it can get hurt. Or when you jump from certain height, you have to lower your legs, otherwise you can get hurt in your knees. That is the application of this law, and is what we spoke about for the same change in momentum. And that is an important fact that you have to use. If and let me write it here, if change in momentum is constant, so for the same change in momentum, the longer the time, the smaller the force. So the seatbelt, what does the seatbelt do? When the seatbelt is holding you through your body, it's increasing the time in contact. It's making the time between you and the car, for instance, longer. And as a result, the net force is smaller. Because the longer the time, the smaller the net force. The same happens with the airbag. When the airbag inflates, what happens is increasing the contact time between you and the car. And as a result, the force acting on you becomes smaller. Guys, it's important. If you hold or you get a ball that somebody thrown to you, you move it backward. You cannot keep your arms just like that. You move backward, you increasing the contact time, and then as a result, the force becomes smaller and then less possibility of injure yourself. The same happens if a ballerina jumps and then flex the legs, it's because you want to increase the contact time and then the force becomes smaller. It's quite simple. I hope it is clear. All right, and then let's practice one question just before we finish this video. We already have for 16 minutes. They say a tennis ball of mass 0.2 kilogram is hit with a racket, changing its velocity from 5 to -5 in 0.05 seconds. Calculate the change in momentum of the ball, the impulse, and the average force exerted by the racket. Guys, let's extract the data here and real fast because time is running. So data. Now, in this case, the mass is equal to 0.2 kilograms. We have that the initial velocity is equal to 5 meters per second. Guys, in this case, they also use two words as positive because you can see that the initial, which is towards the racket, is positive, and the final, which is away from the racket, is negative. So in this case, towards is positive, is an important data, so this velocity or initial velocity is going to be positive, and then the final velocity is equal to minus 15 meters per second. The time is given to us and is equal to 0.05 seconds is the contact time between the racket and the ball. And then we're looking for change in momentum. Let's write here all question marks. We're looking for impulse and we're looking for net force. In this case, they speak about average force, but they are referring to the net force between the racket and the ball. So quite simple. Let's do the change in momentum real fast. This one was in a previous video. This is question 2. Yes, question 2 from the lesson. I'm going to be releasing these lessons quite soon so you can access all the lessons organized 2.1. We're looking for change in momentum. This is the product of mass, final velocity. Let me just fix that one. Final velocity minus initial velocity, and then the rest is substitution. It's quite simple. I didn't want to make a very complicated question at the moment. 0.2, 0.2, and then be careful here with the direction is -15 minus 15 minus 5, and this will be equal to, let me make sure I do not want to make mistakes here. We get 4. This is 4 kilogram negative meters per second. Once more, I don't want to leave that. They're asking you to calculate the change in momentum. It's a vector quantity. I don't want to leave that negative. I rather want to write it in words, so it's equal to 4 kilograms meters per second. away. It means away from the racket. Now, question 2.2, real fast. 2.2, they ask you to calculate the impulse. Impulse is equal to change in momentum. Therefore, impulse is equal to 4, but the unit is not going to be kilograms per second. The unit of impulse is Newton second. So it's Newton multiplied by second, the same direction. There we go, guys. It's quite simple. It's very simple. Be careful with the unit, even though they may give you marks if you write kilograms per second. And to end this question, 2.3, they ask you to calculate the net force. So we're going to apply Newton's second law in terms of momentum. I am going to write it in the same way as is given to you, and the rest is substitution. So F net multiplied by the time, which is 0.05. If I'm not mistaken, let's make sure 0.05, and the change in momentum was calculated, so it's -4. Be careful. In this case, we have to substitute the direction. We said toward is positive, so this one was away, which is negative. Be careful with that one. And then when you calculate, you get that F net is equal to, and let me just -4 divided by 0.05 is equal to minus, oh my soul, I don't know what I want to write, minus 80 Newton. So F net is equal to 80 Newton hour. Guys, this is the end of the video. We did learn about Newton's second law in terms of momentum. We did learn how to apply this one to safety figures, which are very, very important. We learn about the graph. We learn a lot here, guys. I am going to be releasing all this lesson in a document that you can download very soon, and it's also going to be a consolidation material which have 10 questions, 2 exams that you can practice your knowledge. I hope it helped. Thank you for watching. If it helped, thumb up, subscribe for the channel, and I'll see you next time. Mr. G.